Thank you, everyone. This is Gagan here. Just to introduce myself, I work as a research scientist in Google's search ad auction team, or auction/mechanism design for the core search ad business. And today, this is the third talk in our ongoing seminar on market algorithms and design. There are more upcoming talks. We'll paste a link in the chat bar if you are interested in. If you haven't signed up and you're interested in further talks. And so today we have the pleasure of having Professor Ramesh over here. He's a professor in management science and engineering at Stanford University with courtesy appointments in computer science and electrical engineering. He received his PhD from MIT in 2004. His primary research and teaching interests include market design, experimentation, and design of learning algorithms, particularly in the context of online platforms. And interestingly, alongside his academic work, he has also served as an advisor to a number of platforms, including Airbnb, Stitch Fix, Uber, and Upwork. And since 2018, he has been a co-editor of the revenue management and market analytics area at Operation Research. And he has received numerous awards for me to be mentioning here. And also to accompany Ramesh, we also have two guests, Dave and Negin from MIT. And finally, to set the rules, I think depending on the audience. So we have a large audience. Feel free to either unmute yourself to ask a question or even ask a question in the chat, and then I can take the question at the appropriate time. And yeah, I think that's about it. Ramesh, it's up to you.
Okay, great. Thank you, Gagan, and thank you to you.
If I may interrupt, we should introduce our guests, no?
Hello.
Sure. Thank you.
So we have Dave and Negin from MIT who are accompanying as guests.
And thank you guys for having us. It's a pleasure.
Yeah, definitely. Thanks for having us.
Yeah, thank you both for doing this. And thanks to Yash and Judy and Daniela and Gagan for organizing the seminar, obviously. It's great to have a chance to present some of this work. So this is joint work with Hannah Lee, who is a graduate student in Stanford Management Science and Engineering, working with Gabriel Weintraub and myself. Gabriel is a professor in the GSB at Stanford. And also with Ines Eliskovic, who's a data scientist at Airbnb. And the title maybe is a little bit too broad, frankly, that it's based on a paper where there's a colon analysis of bias after the title, and you'll understand that better after I get through the talk. At a high level, the kind of main motivation for our work is that all kinds of platforms use A/B tests, experiments to test new features. Usually the goal of such an experiment is that you're interested in estimating what's called the global average treatment effect, which is the difference between global treatment and global control. And usually, when you think about A/B tests, kind of the common examples are all sort of things that are fairly simple. So it might be like, for example, changing a color in a web page or something like that. And you're interested in seeing, is the control of red better than the variation of green or worse? The thing in marketplaces is that there's a kind of complicated effect that arises because if you randomize among demand, so let's say you allocate some users to treatment, some to control, they're competing for the same set of supply. And similarly, if you randomize on the supply side, they're competing for the same set of demand. And this can lead to interference and thus biased estimates from these tests. So I want to, just to make sure that everybody is on the same page, I know for some of you, you may be familiar with these types of effects, but I just want to drill down a little bit more into kind of where this interference arises from competition with a overly simplified example. So think about an online labor platform where you have a freelancer and you have two customers. Suppose that what we do is we're interested in testing a new intervention, and we're going to do that by randomizing customers into treatment or control. So in particular, the treatment has the property that it's going to make customers more likely to book. In this example, customer A has been randomized to treatment and B to control, and therefore customer A is going to be more likely to book. So let's say that customer A books the freelancer. Freelancer goes away, A goes away. So now customer B essentially has no supply available to book. So if we naively estimate what is the difference between treatment and control here, we would find that A booked and B didn't book, and therefore, we would certainly observe that A was more likely to book. But the problem is that we would overestimate this effect because the available supply for B to book has gone down solely because of the fact that treatment customers book more frequently. So this kind of, pollution of the supply pool available to one group because of the presence of the other group is exactly what we refer to as interference in experiment design and analysis. And in this particular case, what we find is that competition can lead us to underestimate bookings in global control and overestimate the bookings in global treatment, and therefore obtaining a biased estimate. I just want to point out as an aside, by the way, most of the time, I would say that when we're thinking about these kinds of things, and most of the natural examples you're going to think of, they're going to look like you're getting kind of the right sign of the effect, but that the bias is inflating that effect, the magnitude of the effect, or deflating the effect relative to what the correct value would have been. There are examples where the sign itself can be wrong as well. And happy to sort of discuss that with others offline or through some of the questions here. So in terms of the size of this bias, there's ample evidence at this point already, even in the academic literature, that the bias can be as large as the treatment effect, which of course is a massive problem. And I think this is something where I'm mentioning a couple of papers here by Blake and Cui and by Fradkin, but frankly, it's something that anyone who runs these experiments at platforms would be familiar with the fact that these biases can be quite large. So not surprisingly, platforms have heuristics for how they might reduce bias. There's been a lot of work on methods that involve clustering. In particular, there was work on graph clustering in the kind of network interference community, where people focused on experiment design on networks. And some of that you could apply in marketplace settings as well. Many marketplaces, especially those focused on delivery, ride sharing, et cetera, will use something called switchback testing, where you basically keep the entire platform in treatment for some period of time, then switch the entire platform to control and back and forth. I guess I would be remiss if I didn't mention that despite all of these heuristics, the prevailing norm is still to run experiments by randomizing on one or the other side of the market and accept that the interference exists. It's actually relatively less common that you run these types of more advanced methods that try to correct for interference so far. And I think this is one of the reasons this is such an exciting research area. And so kind of wrapping up the slide, I think the kind of overall sense that you should take away from our current understanding is that we lack consensus on when biases can be especially large, or what types of designs or estimators minimize bias and variance. And that was kind of what motivated our work. So I think one thing I'd say at a high level about our work is that it's, to me, it's sort of an appealing approach to thinking about some of these problems, because we're dealing with kind of complex systems from an operations point of view. And one of the things I think the operations community is good at or likes to do is to build formal frameworks within which we can understand performance and trade-offs of different designs or approach to analysis. And that's exactly the approach we take here. Essentially, one of our goals was to build kind of a formal model within which we could actually provide some structured understanding of how different experiment designs and estimators perform, what their bias looks like, and ultimately obtain insight towards design of better experiment designs and estimators. So I'd say there's three main takeaways I want everybody to kind of walk away with. The first one is that a key quantity that we're going to focus on is the relative imbalance between supply and demand. And in particular, I'm going to try to show you how the biases of common designs and estimators, those that randomize on one or the other side of the market, depends on supply or demand imbalance. And then we're going to introduce a novel approach to randomization that involves actually randomizing on both sides of the market simultaneously, as well as discuss a couple of associated estimators that are suggestive of an approach to reducing bias in some of these large two-sided market settings. And then finally, we'll wrap up. Hopefully, there'll be time to just briefly talk to you a little bit about kind of our current understanding of variance. And really, that last bullet is the only reason that I didn't have analysis of bias in the title. I also want to tell you a little bit about how the variance of these things behaves. So maybe before I go to the model, this is probably just a good point to pause, given that we're all on Zoom, and check with Gagan or others if there's any questions.
I think people can raise their hand in the Zoom if they have questions, or they can ask in the chat.
All good?
Oh, yeah, we're good, I think. Ramesh, you can go
All
ahead.
right, cool. Let's keep going. Okay, so let me start by describing the model. And the model, essentially, our goal was to capture dynamics in a two-sided market. I would say, the maybe important thing to take away here is that a major goal of the model was to capture inventory dynamics. And it'll become clear what I mean by that as I go along. So, okay, first of all, the model consists of a two-sided platform in continuous time. And I'm going to talk about customers and listings as the two sides of the market. Customers are the demand side, listings are the supply side, and customers book listings over time. So the inventory constraint comes from the fact that the number of listings is fixed at this value n, okay? And we're going to think of a scaling regime of the market where this n approaches infinity, all right? So that'll be kind of a key element of the modeling that we do. So within our model, it's fairly general in the sense that we allow listings to be heterogeneous. There's this type theta that's a finite type set. And I'm going to assume that there's convergence of the fraction of listings of each type as the number of listings scales. So in the limit model, rho of theta will denote the fraction of listings that are of type theta. Importantly, we don't really do much in the paper where we distinguish between observable and latent type information. In practice, of course, if you have some observable information, you could probably do something more sophisticated with that. Instead, we kind of assume that the platform isn't using any information about types in determining sort of how it's going to go about analyzing the experiment. And so from that perspective, in particular, I guess an important point to make here is that the model is fairly general in the sense that these types could even be latent, and everything I'm going to tell you is still going to go through. Okay, so what is the state of the market? Now, at each time t, a listing can be either available or booked. And so here in this picture, I've got some that are kind of in bolder color. Those are available listings. And some that are in lighter color, those are booked freelancers, booked listings. Okay. And so, what happens over time, the inventory dynamics are that listings move in and out of being available and booked. So I'm going to use sigma t of theta to denote the number of available listings of type theta at time t. And I'm going to use bold sigma t to denote the state of the system at time t. That's just the vector of how many listings of each type are available. Again, note that if the type theta is latent, this state may not be fully known by the platform. Okay, so it's important that I'm not building estimators off of the full state. But as far as our analysis of the system is concerned, this is the object that we're going to work with. There's another sleight of hand going on here. It's not obvious at all that this state is a sufficient statistic for the market. And so I need to fill in the rest of the dynamics here to convince you that I'm coming up with a model where this indeed is a reasonable state representation. So far I've told you listings can be available and booked. I haven't told you how they become available and how they become booked. So that's kind of what we're going to walk through next. Okay. So the booking process obviously involves customers booking listings. How does that work? So customers arrive over time. And upon arrival, two things happen. So the first thing is that, remember, the state of the market is how many listings are available of different types. And the first thing that will happen is that the customer will sample a consideration set from the available listings. So the consideration set is kind of the universe of objects from which the customer may make a choice. Right? They don't have to book, but if they do book, that booking is going to happen from out of this consideration set. And so that's the next step, which is that they'll choose which item, if any, from the consideration set to, that says rent, I should say book. Essentially, which item out of that group are they going to take off the market? Okay. All right. Now, again, just like with listings, customers have types in our model as well. Again, the types can be latent, and again, this type set is finite. So just as I was saying earlier about the difference between observable and latent type information, again, in our model, we don't really use anything about customer type information in the estimators that we study. And so, essentially, it doesn't matter from the perspective of our results whether the type information is latent or not. OK, so customers of different type, they arrive potentially at different rates according to a Poisson process. And so I'll index the the arrival rate by gamma, the customer type. In general, in our notation, customer type is a subscript, and listing type will be parenthetical. Will act as an argument. OK, so what's kind of the important quantity that's going to govern how listings get taken off the market by customers? Pretty clearly, it's that there's some state of the market. The state of the market leads to some consideration set that leads to a choice of what item to rent or what item to book. And in turn, that leads to that item becoming unavailable, that listing becoming unavailable. So our interest is in that choice probability. That is the choice probability that an arriving customer of a given type, gamma, rents a listing of a given type, theta, when the composite system state is sigma. Remember, sigma is a vector. It's a vector consisting of the available listings of the number of available listings of each type. Okay, so in our paper, we make a specific set of assumptions about the choice model. And I think just by way of backing up for a second and providing some higher level perspective, I think this is a place where there's lots of room to do interesting stuff, both on the empirical side and on the modeling side. We made some particular choices that I think are not unreasonable. And like I said, the model is fairly general because type information is allowed to be general. But nevertheless, you'll see that there's a couple of things in here that are important as far as the model is concerned. So, OK, let's suppose that a customer of type gamma arrives. And the set of available listings in the market is this set of 6 listings. The color denotes the type. So there's 1 listing of yellow type, 3 of blue type, and 2 of green type. And they're all kind of in bold color right now. They're all available. OK. So the first step is that the customer forms a consideration set from the set of available listings. That process takes place by independently sampling listings of each type, right, with a probability that depends on the customer type and the listing type. So essentially, we have 3 listings here that are of type blue. So there'll be alpha gamma blue is the probability that a listing of type blue enters the customer's consideration set. The customer independently determines on each one with that probability whether or not to include it in the consideration set. So in other words, the number of blue listings that enter the consideration set is a binomial random variable with 3 samples and this probability of success. And same for green, same for yellow, right? This is independent across listings, so that's an important assumption. And let's say in this case, this leads to this consideration set where yellow enters the consideration set. 1 of the 3 blue listings enters the consideration set. 1 of the 2 green listings enters the consideration set. Again, just so that people don't get misled, by the diagram, it's entirely possible that 2 or 3 blue listings could have entered the consideration set, or 2 green listings could have entered the consideration set because it's a binomial random variable. Okay, or 0 actually, for that matter. All right, now the customer has a consideration set. At this point, the state of the market is irrelevant. So the state of the market only matters up to the extent that it determines what the consideration set looks like. Once the consideration set has been formed, the customer chooses from this set according to a multinomial logit model with some outside option value that depends on their type, right? And V denotes the utility of a type gamma customer for a listing of type theta, and E sub gamma denotes the outside option value that the customer has when they're of type gamma. Right? So let's say that in this case, they decide to book the green listing. Then the green listing becomes unavailable from this original set. And now what you're left with is that the other 5 listings are available, but the green listing at that moment in time is no longer available. And again, it's a multinomial logit choice model. The outside option values are all positive. And so in particular, another possibility here is that the customer might have chosen not to book anything at all. OK. So the first thing I want you to notice, I'm going to make 2 comments in this slide and the next one that I hope will feel fairly obvious, but are going to be extremely important when we start thinking about interference. The first thing I want you to notice on this slide is that clearly there is competition between listings, very mechanically, because the presence or absence of other listings will alter the probabilities of booking by the customer, right? Even though we're independently sampling across listings to determine whether they enter the consideration set, ultimately, because the consideration set leads to choice through competition between these listings, there will be competition between the listings that are present in the market. Okay, so that's kind of an important thing to take away, and that would pretty much be true of any reasonable choice model that you can think of. And that's going to play a role when we think about how interference can arise between listings. Something else I want to point out, some comments on the choice modeling here. I think obviously the independent selection is an important point in the design of this model. You could think of something else where, for example, there's some nonlinearity in the customer's, in the number of such items that will be included in the customer's consideration set. And in that case, maybe it wouldn't be the case that you independently are sampling across individual listings. There's many other ways to think about how that could be, how consideration sets could be formed as well. And then the other thing I want to mention is that the multinomial logit choice model, of course, also includes additional assumptions. For example, it satisfies independence of relevant alternatives, and that may be something that we think could be violated. I will say that some of these concerns are mitigated because of the generality of the type modeling. So in particular, we actually have kind of a nested logit choice model because there's customer types that are heterogeneous. And then another thing I think I would mention is that, in fact, because alpha is allowed to depend on the customer and the listing type, at least it allows us to capture things where different customers of different types may see listings, more or less prominently on the site, and therefore that would change the probabilities that these listings get selected into their consideration set. So that lets you capture things like search rankings or recommendations or something that alter probabilities in a type-dependent way in pairs of customer and listing types. So I guess this is all just a long-winded way of saying that although there is some significant structure in the choice of independent consideration set construction and the multinomial logit choice model, the generality of the type modeling, I think, at least compensates for some of those things. But yeah, nevertheless, I think that is an important area to think about for future work.
We have one question from Sarah. Sarah, yeah. Can you unmute yourself and ask the question directly?
Oh, sorry. So I guess you answered some. So I was wondering if the goal of the step of making the consideration set was to trim down the set of items for the multinomial logit, but then you talked about customer preferences and search ranking, and that kind of answers it. But is there more to that?
Yeah, wait, sorry, just to make sure I understand the question. It's sort of what's the goal of going from consideration set to multinomial logit? I suppose you mean as opposed to just directly to multinomial logit. Yeah, that's a good question, actually. I mean, I think essentially there's two answers to that, okay? One of them, I guess, is the sort of tractability answer. Like, how does this give us tractability? And I'd say the main way it gives us tractability, and you'll see this in a second, is that it creates a very structured dependence on the state of the market. So in particular, the state of the market plays a role primarily in that first stage. And in general, you could think about a choice model where you have kind of a highly non-parametric dependence on the state of the market. And one of our goals to get structural insight was to have something where that's more tractable. But yeah, I think, once you get past that, then you think about, well, what are other reasons why this is useful? I do think, from a practical standpoint, there are reasons why you might want to estimate these two parts of the process differently. The set of algorithmic choices that the platform makes that determine what the consideration set looks like, and then the estimation of a demand model given the set of items put in front of a customer, they do feel like processes that are often carried out separately, within like the organization of data science in a platform. So there's probably, good practical reasons for thinking about things that way as well. Often they can be hard to disentangle for other reasons, but yeah.
Thank you.
Thanks, Sarah. Ramesh, we also have more questions if you can take now, or?
Yeah, sure. Let's go for it.
Varun or Catherine, one of you can, actually both of you can unmute yourself and ask the question directly.
Sure. I'll go first. Hi, Professor Johari. I just have a quick question. In terms of, do we take into account of any explicit price vector or like budget constraint in the setting of this?
Oh, that's a great question, and it's easy to answer too. No, we don't explicitly study the role of price in this paper, and I think that is a great and very interesting direction to take things in. One paper I want to highlight that I think does really nice work with sort of interference related to price experiments is work by Stefan Wager and Kwang Zhu. That looks at kind of long-run equilibration in response to price changes. And so I think that's a very nice piece of work. And I think there's a lot more to do in that direction as well. But yeah, this paper does not have any explicit consideration of specific treatment on price, or
Got
what the way that may play through the model. Yeah.
Thank you.
Thank you. Varun, you want to go next?
Yeah, I think a quick question. So suppose the user said, okay, I want at least like 2 yellow and at least 3 blue, then somehow the role of competition goes away. So would the message also sort of get diluted in that case where the choice, the selection model was somewhat different?
So you mean where, do you mean where the customer had like a minimum, like a cardinality constraint on how much of each type of thing they wanted?
Right.
I think what I heard you say is that would mitigate the competition concern. I'm not so sure about that, right? That's changing the process of consideration set selection. But remember, the competition between listings is primarily happening through the fact that ultimately you're making one choice out of that set.
Okay.
It may be that what you meant is that customers are buying bundles of things. And of course, then, yeah, you have a different competition model in that case. There'd still be competition. I think as long as limited inventory is changing, is affecting the dynamics, you're going to have these effects.
I see. Thanks.
Okay, let me keep going. The booking dynamics. So if the customer books the listing remains booked for an exponential period of time with parameter tau of theta. And then, the key thing in our model is that because that's an exponential time with some parameter, the listing may still be booked into the future, even when subsequent customers arrive. And that, pretty clearly creates competition between customers. So basically, the fact that I'm present in the market buying something and taking something off the market for some period of time, if you come after me, there's a chance that my actions have eliminated some inventory that's available for you. So this competition between customers is virtually identical to what I showed you in the really caricatured example on the second slide, where customer B had nothing left to book because customer A took something off the market. Okay. All right. So now I can cycle back. You remember I told you need to hold me to the standard that sigma t has to actually be a meaningful state for the system. And I guess the thing I would note there is that the way we set up the choice model actually makes it so that sigma is the current vector of available listings of each type is a sufficient statistic for the state of the system. So in particular, with that plus this exponential booked time, what I get is that the sigma t is a continuous time Markov chain. And actually, if you want to think of it this way, for those of you that are in operations, this is essentially a relatively complicated form of closed queuing network where you have n things that are cycling in and out of being booked. And whether or not they get booked depends on sort of important characteristics of the state of the system. And so, the choice model that I gave you, although it's structured, it's difficult to analyze because there's still these two stages. And when I say difficult to analyze, what I particularly mean is that there's a complicated way in which the choice model is influencing state dynamics. So what we do, and I hinted at this earlier, is that we consider a limit where we take the number of listings to infinity. I won't obsess about these two conditions here, but basically we're taking outside option scaling so that it normalized by n converges to some well-defined value, and the arrival rate scaled by n is converging to some well-defined value. And you might remember earlier, I told you that the fractions of listings of each type are also converging to some well-defined value. So, kind of the first thing that we observe is that in that limit, what happens is that if you have a sequence of states where the normalized values of those states is converging to some vector S, so now notice that S will be the masses of available listings of each type, as opposed to cardinality of available listings of each type. Then what you could show is that this complicated choice probability R, for which I couldn't really write down any meaningful form for you, converges in the limit to something that becomes a relatively nicely structured multinomial logit choice probability. So back to Sarah's question, one way to think about what's happening here is that when we pass the mean field limit, indeed, we actually do get just a single multinomial logit choice model to describe exactly how customers are going from state to what to book. But this multinomial logit choice model has some important structure in it, namely the utilities are linear in the mass of available listings of each type. And that kind of is key in allowing us to do some of the things that we do analytically in the paper. Okay, and in particular, here's kind of the main way that helps out. What we're able to show is that now if you look at the entire process, that converges to an ordinary differential equation. Not important to obsess about the terms here. Basically, the important thing is that the number of available listings or mass of available listings is kind of balanced between two terms. There's a replenishment rate, which is the rate at which listings come back available of a certain type. And there's a booking rate, which is the rate at which listings of a given type get taken off the market. For our purposes in this talk, what's important is that this has a unique limit when t goes to infinity, okay? And so I've noticed that I took n to infinity first, and then I take t to infinity in that limiting ODE. So that unique limit, I'm going to call the mean field steady state, or most of the talk, I'll just call it the steady state. And that object, it's an S star. You can think of it as an S star, a single vector of masses of listings that describes in steady state what's the mass of listings of different types that will be available, right? And in case you're curious about the proof, we use Kurtz's theorem to establish this mean field limit, which is a standard tool for proving convergence of stochastic processes to their fluid limit. And we build a Lyapunov function for the limiting ODE, where kind of the key idea in the Lyapunov function is that the log sum x function is an integral of this multinomial logit choice model. Okay. All right. So enough of the technical details. What do we have? Basically, let's say that you zoned out for the last 20 minutes or so. The main takeaway up to this point is I built a substrate on which I can work out the dynamics of the market as a function of these market parameters, these primitives, the utilities, the outside options, the arrival rates, the holding times. And then in turn, what I get back from that is a relatively easy to characterize steady state of the market in the mean field limit. So that steady state object, everything we have to say about experiment design is going to happen through that steady state object, right? And so that's where I want to go now, and is focus on how do we do that. So basically, for the purposes of what we do, we focus primarily on interventions that are going to change the choice probability through one of these three things. It can change the probability that a listing is included in the consideration set. It can change the utility of an outside option, change the utility of listings. And just one thing I'll mention here is that this epsilon gamma, everything I'm talking about here, the alpha gamma and V gamma, we defined at the outset, and epsilon gamma is that limiting value of the outside option in the mean field limit. So, in the mean field model, we consider interventions that can change, any of these three things. Okay. And, an important thing that I won't really dwell on is that essentially without loss of generality, we can just go ahead and focus on interventions that change C. It turns out that interventions on the other two can basically be recast as interventions that are just changing the utility of a particular type of customer for a particular type of listing. So that's what we're going to focus on, is interventions that change that. Okay. And the platform's question that we focus on in the paper is how the intervention, this change in utility, changes the steady state booking rate in the market relative to the baseline. Now, remember, I'm phrasing this kind of fuzzily, but going back to the very first slide, the platform is interested in global treatment and global control. Okay, so the platform is going to be interested in at least two worlds: one where every customer sees every listing as control, and one where every customer sees every listing as treatment. Okay, so the central challenge in experimentation, this is kind of a version of the fundamental problem of causal inference, is that the platform is going to reason about these two worlds through an experiment where some customer listing pairs are in control and others are in treatment. And which ones are which depends on the design of the experiment. I'll walk through some designs in a second, right? So the platform's goal is to compare what the booking rate of listings would have been in the global treatment condition against the global control condition. But it's going to have to do that through a single experiment. And, our goal is to understand how these experiments and associated estimators do in estimating that desired quantity. Right? So just a couple notes on how this maps to the model. And unfortunately, just because of time, I can't spend as much as I should probably to explain this. So I'll just say it at a high level. What the model lets us do is take any primitives we want and simulate the market out to get this mean field steady state, or essentially like run the ODE to get this mean field steady state. And we have a nice characterization of what that looks like. So the way we map global control and global treatment to the model is kind of obvious. Global control set all the parameters according to what they would be in control. In particular, all the utilities are the control utilities. Global treatment, similarly, it's set all the parameters according to what they would be in treatment. All the utilities are the treatment utilities. The trickier one is the experiment, where some of the utilities are control utilities and some are treatment utilities. So the way we handle that is that we essentially create duplicate types. So for every original type, we create two types. There's a control type and a treatment type for both users and listings. And now, depending on the experiment design, the utility when a customer of a certain type interacts with a listing of a certain type is determined through either the control or the treatment utilities. And I'll explain that as I go along a little bit. But that's roughly the idea of how we're able to take our model and then embed experiments within the model. And then all the dynamics flow accordingly. The theorem basically carries over exactly as I had stated earlier. All right. So what is this unknown parameter of interest? Getting a little bit more precise, it's that when everybody sees the intervention, you have a steady state rate of bookings and global treatment that's going to be denoted QGT. And when everybody sees control, you have a steady state rate of bookings and global control that's QGC. We're going to focus on the difference between these two things as the global treatment effect, or the global average treatment effect more precisely. So QGT minus QGC. Just an aside, platforms will look at sometimes ratios of these things. That's probably not that critical in terms of what I'm talking about here, exactly how you choose to measure the global average treatment effect. So we're going to start with two canonical designs that are used everywhere, like I mentioned, which basically just involves randomizing on only one or the other side of the market to estimate this quantity. I just want to say it one more time just to make sure there's no confusion. This quantity is a single number. And essentially what we're doing when we run this experiment and build an estimator is we are trying to come up with an estimator that is estimating the single number. So when we talk about bias, we're going to be asking how large or small is our estimator relative to this true quantity. Okay. All right. So let's start with customer side randomization. Just for the purposes of illustration, I'm going to think of an example here where listings and customers are homogeneous pre-treatment. All our theory goes through for that fully heterogeneous model that I showed you at the beginning, but this is just easier to understand. Okay, so suppose you have a customer that arrives. The customer gets randomized into treatment or control with probabilities AC and 1 minus AC respectively. And because everything is homogeneous, the only thing I need to tell you is what's the utility when the customer is a treatment type, what's the utility when the customer is a control type, because there's only one type of listing. So V tilde versus V are those two utilities post-treatment condition for listings. And so when a customer of treatment type sees the market, they see a collection of listings that all have utility V tilde. When a customer of control type sees the listing, they see a collection of listings that all have utility V. Notice that these customers are seeing kind of the same market in the sense that there's 5 objects available. It's just that the utility that the customer is going to have for each of these listings varies depending on what their treatment condition is. Okay. And as I noted earlier, here you're going to have competition between customers, because if one customer comes to the market and V tilde, let's say, is higher than V, that's going to make that customer more likely to book a listing, in turn removing that listing from availability, at least temporarily, for subsequent arriving customers. So this is why I was saying earlier, there's an immediate carryover of competition between customers and competition between listings into interference. So competition in a market corresponds essentially to interference in an experiment. And I think that's kind of a nice, maybe obvious, but nice insight. So once platforms run experiments like this, they typically compute what I'll call the naive estimator. It's a type of Horvitz-Thompson estimator, which in our case basically corresponds to the steady state rate of bookings by treatment customers divided by AC minus the steady state rate of bookings by control customers divided by 1 minus AC. Just a small technical note here. Something I'm suppressing is that maybe what we should really be doing is dividing by lambda AC and lambda 1 minus AC. And we do some of this normalization both in the paper and in some of the figures I show you, but I'm not going to obsess about that. Because that's just changing by constant. The main thing we would do the same normalization for both the true GTE and any of the estimators we carry out, so it doesn't affect the bias. But the main thing I want to point out here is that, of course, there could potentially be an asymmetry between the massive treatment and massive control customers, and so that's why we're dividing by the respective masses. Okay. So why is this naive? It's naive because, as we said, the rate of booking of one or the other groups could be either excessively inflated or deflated relative to what it should be in global treatment and global control, respectively. Okay, so here's our first important finding, which is that if you use customer-side randomization, the performance is heavily dependent on the market balance. And in particular, if you pass to the limit when lambda over tau goes to 0, in particular, for everything I say here, it's useful to think of tau being fixed. Just imagine lambda becoming small. Okay, Or, actually, it may be that for what I'm about to say, it's easier to think of it as lambda fixed and tau going to infinity, whichever one's easier for you. So the demand constraint limit is something where arrival rates of customers are relatively small, essentially. And first, let's just look at the plot. This is the plot in the mean field limit for a homogeneous model, where essentially as we bring lambda over tau down, the bias as a fraction of GTE is going down considerably. Okay. So what's happening here is pretty easy to explain. And one of my goals for the talk is that the two insights about how these biases arise, hopefully you walk away feeling like they're relatively straightforward to internalize, even if none of the math makes sense. The idea is that if you think about a setting where relative to the customer arrival rate, tau is relatively large, so listings are regenerating quickly between customer arrivals, then what it means is that from one customer's perspective, it doesn't really matter much what the customer who came before me did, because the market will almost completely regenerate and give me full availability back when I show up. So what happens is that that competition between customers that's happening over time gets weakened considerably when you're in this limit where lambda over tau is small, right? And so essentially the idea there is that when you move to that limit, the listings regenerate, and regenerate, I mean they become available again quickly. So whether or not customers before me booked something matters less and less and less, right? That's something that we think, again, it should be a fairly general phenomenon. So one of the things we're doing in our ongoing work is basically generalizing this result outside of just the model that I presented here. OK, what happens on the other side? So what's listing side randomization? Again, let's look at a simple illustration where listings and customers are homogeneous pre-treatment. OK. So we start with, again, just let's look at what happens to an individual listing as it goes through the randomization. It gets randomized to treatment type with a probability 1 minus AL, and to control type with a probability 1 minus, treatment type with probability AL, control with probability 1 minus AL. And again, the post-treatment utility depends on the type. So what does this mean that I see V tilde versus V? What it means is now if I'm an arriving customer and you put a treated listing in my consideration set, I view that listing as if it had utility V tilde. And if I'm a arriving customer and you put a control listing into my consideration set, I view that listing as if it had utility V. So in particular, when a customer arrives, some listings in the market are going to be of treatment type, some will be of control type. And so the customer will view some of them as having utility V tilde and others as having utility V. And of course, as we talked about earlier, there is competition between listings here, because when these listings enter the consideration set, some will be treatment, some will be control. And now that means that whether or not I book a control listing depends on the presence or absence of treated listings. Again, competition leads to interference. Here's the corresponding naive estimator. Same idea. Look at the steady state rate of bookings between treatment and control and take the difference. OK. Well, one thing that was really cool is that there's a striking symmetry here where the listing side randomization estimator behaves well in the limit, in exactly the opposite limit, where lambda over tau goes to infinity. Okay, and here in the graph, I've got blue is the bars I showed you earlier for the customer side randomization, and I've overlaid on that orange for listing side randomization. You can see the bias decreases when lambda over tau gets large. This one takes a little bit more thought, but again, like I said, my goal is that you walk away with some basic intuition for why this is happening, even if the math isn't easy to unpack. So, okay, where does interference come from in a listing side randomization experiment? That's kind of the first thing you have to emphasize, which is, as we've said multiple times, that interference arises because there are competition effects between treatment and control listings, right? So if we were going to claim that the bias was low, then that should be because we've shown you interference is low, which should be because we've shown you the competition effects are low. So competition effects can only be low if, as a single listing of either treated or control type, I'm not affected by the presence or absence of other listings from the other treatment group. And what happens is that when supply is low, then the number of listings that can show up in the consideration set is rapidly dropping. And in particular, in the limit where lambda over tau becomes large, especially it becomes as large as going to infinity in the asymptotic we're taking here, you essentially reach a point where effectively it's as if when I become available, I don't have any other competition in the market. So now when I enter a customer's choice set, it's quite likely I'm the only thing in the customer's choice set. There's a little bit of a problem in thinking of things the way that I just described them, because formally, remember, we pass to the mean field limit first, then we take lambda over tau to infinity in the mean field limit. But I think the intuition comes from what I'm saying, which is that essentially what's happening is that when lambda over tau gets very large, then a single listing faces less and less competition from other listings. So just a small aside I want to point out here from a practical standpoint is that although these two results are symmetric, right? There's this one for listing side randomization and this one for customer side randomization. I think that it's important to note that the idea you're going to find yourself in an extreme where a listing never sees competition from other listings is relatively low, I think, compared to the possibility of being in the demand constraint limit, relatively speaking. So I think that's an important practical question about calibration. I'll come back to that in the last slide. OK, so finally, let me talk about a new design, which is two-sided randomization. And so in two-sided randomization, we do kind of the obvious thing that comes out of what we just said. Though obvious, it's surprising that this isn't done very much, which is to randomize customers into treatment with probability AC and randomize listings into treatment with probability AL. Now, if you do that, something you have to talk about is, well, if both of them are being treated, what does treatment really mean? So in the paper, the TSR designs that we look at are something where the treatment intervention only applies when both the customer and listing are in the treatment cell. So that's this like green cell that I have here, where both treatment applies to customer and listing. And in any of the other three cells, the control experience is obtained. So the utility is the control utility, all right? There are other TSR designs you could imagine. For example, this is something where I take an and of the treatment condition. You could do an or of the treatment condition, in which case the only control experience would be in the upper left cell, for example. I just want to point out that there's also independent work by Pat Bayari and Hito Imbens and co-authors that looks at something they call multiple-sided randomization that is similar to what we're talking about here with two-sided randomization. So one maybe last comment I'll make about two-sided randomization before I show you some results is that kind of obviously this generalizes CR and LR. Essentially, if I compress the control listing group down to 0 or the customer control group down to 0, I recover each of the two designs. So CR is the randomization where AL equals 1. All listings are in treatment. And LR is the TSR design where all customers are in treatment. And so what we would expect is that because of this generalization, we're at least able to get some benefits of each. And that's kind of where we head. We start out by defining just a naive TSR estimator, which is basically the steady state rate of booking in the treatment cell against the steady state rates of booking in the control cell, in the blue cells. Okay. And what we want is to somehow recover the benefits in these two different market balance conditions. So to get there, what we do is we define these things we define the randomization probabilities, AC and AL, to interpolate between customer and listing side randomization based on the market balance. We use a heuristic for this in the paper that I won't really get into. It wasn't as if we've necessarily optimized that in any way. But the goal is that you would essentially approach CR when lambda over tau gets small, and you would approach the LR design when lambda over tau gets large. So with that kind of a TSR design, not surprisingly, what we obtain is that we can show that kind of interpolating design is unbiased actually in both limits. So it kind of gives you bias mitigation across a wide range of market balance if you're able to tune accordingly. Okay. Now, maybe one other comment I'll make that's a bit more subtle is that actually two-sided randomization has a lot more power than just what I told you there, which is this like interpolation idea. In fact, two-sided randomization carries within it more information about the nature of cannibalization. So to get a sense of that, let's look at this table again, and let's look at differences in the control customer group of the rates at which they book control listings and treatment listings. Now, a control customer can't tell the difference between these things. So to the extent that there's a difference in these rates, it could only have been because these listings were cannibalized away. For example, if V tilde is bigger than V, those listings would be booked at higher rates in the green cell. So there would be less of them, relatively speaking, available than the control listings. And so, if we see control customers booking these listings at different rates, that's telling us something about the magnitude of cannibalization. And kind of the same thing on the treatment side, on the listing side. So, what we do in the paper is we add a heuristic that tries to account for these two types of competition effects, customer and listing competition, and add that to the two-sided randomization estimator. And that actually turns out to give additional benefits on bias beyond what I just showed you. Okay. So I think I'm running a bit short on time, so I'm going to wrap up here with just a quick discussion of variance, because the entire paper is about bias, and I think it's important for us to tell you a little bit about how the variance of these estimators performs. What we did is we simulated a system where n is 1,000 to study variance of the estimators. And we looked at something where we have a 20% booking probability in global control and 23% booking probability in global treatment if the market's balanced in the sense that lambda equals tau. So the simulation is outside the mean field limit. And so we can talk about sampling distributions of the estimators that we're proposing. And kind of what I want you to take away from this plot, really the only main takeaway, is that the standard error of the two-sided randomization design is not appreciably different from the customer or listing side standard errors. There is a little bit of an issue here in the sense that I'm showing you the true standard deviation of the sampling distribution. Of course, there will be a difference between that and naive standard errors that you would compute in practice using the data that you got from the experiment. So that's actually something we're actively working on, which is to think about how you should be computing standard errors in practice for these different designs. But at least as far as the sampling distributions are concerned, it seems like we're seeing bias mitigation across the entire range of lambda over tau, but without an appreciable increase in the variance. Okay. So just to wrap up, and then I'll leave it to David, Negin, and others. Happy to answer more questions. Our work is really focused on providing a structural model to understand bias in two-sided experiments. And then, as I said, we introduced this novel family of TSR designs that mitigate that bias. There's a bunch of exciting, future work that comes out of this. Hannah, unfortunately, only has one PhD she can do, but this is something that there's so many different exciting things that we could follow up on. So, one thing we're actively thinking about is how to calibrate these experiments using market observables, demand, supply, arrival rates, et cetera. We are thinking quite a bit about what good TSR designs are. To be totally honest, in the paper, we haven't really focused on optimization of TSR designs, and I think that's an important area of future work. Besides using TSR designs themselves to estimate the treatment effect, you could use a TSR design to act as a debiasing tool for naive LR and CR estimators. And that's an open question as well. How could you use the output of a TSR design along the lines of this cannibalization estimate I told you to debias naive designs? And then finally, there's obviously lots of work to do on empirical validation, actually moving towards implementation and using simulations to show quite a bit more about how these different estimators and designs perform in different situations. So I'll stop there and take questions and comments. Thanks, everyone.
Thank you, Ramesh. Anyone has questions?
I have one question for Ramesh. So first of all, thank you very much for the great talk. So my question is about this experimentation. You talk about A/B testing. I'm just wondering if one can, for example, how one can use the funding of this paper if they want to deviate from A/B testing and, for example, go with something a bit more sophisticated like Thompson sampling.
Okay. Yeah, that's a great question. And I think, your question, honestly, and again, that's even broader just than what I talked about here. We could even talk about that in settings where experiments don't have interference of the type I brought up here. Mm-hmm. I think the main issue with using things like multi-arm bandits for experimental analysis is that you have adaptive allocation. And adaptive allocation means that there can be bias in your estimates of treatment effects because essentially the chance that you pull an arm was dependent on what you saw in the past. Mm-hmm. There is a lot of work, I think. There was a seminar in the online causal inference seminar series on batched bandits, which is kind of a natural way of allowing you to carry out statistical inference of the classical frequentist sort while running a multi-arm bandit. So there's definitely been a lot of progress on that front. And then, I think coming back to the setting I'm talking about here, that's a super interesting question, I think, where I mean, in particular, in practice, what people often do is roll out interventions progressively. You start at a low allocation and then gradually allocate it more and more and more to the rest of the market as you see if it's doing well, which basically, again, is a form of adaptive allocation. And, I think being able to give platforms guidance on how they can do so while having sort of, unbiased estimates of performance along the way, I think, that's a great point of intersection between these topics. I guess it's just a long-winded way of saying I don't have a great answer for you.
That was good. Thank you.
And we have, so Maxime and you guys can actually unmute yourself.
Yes. So hi, Ramesh, a very nice talk. So going back to the bias plot, you show that when there is a perfect balance between supply and demand, there is still a little bit of an edge for the TSR.
Let me see here. Right here, right? Yep. Okay, go ahead. Sorry, Maxime.
When lambda over t equals 1,
yep,
there is perfect balance. There is still a tiny edge for the TSR. Any intuition of what is happening?
Okay, yeah. So, once you start bringing the skeletons out of the closet, all kinds of funny things can happen. So the first thing I think I should say is that lambda over tau equals 1. You shouldn't necessarily think of that as perfect market balance, because really, it's hard to define exactly what perfect market balance would look like. All that means is that the inter-arrival time of customers is the same as the holding time, the mean holding time of a listing, right? But that's not necessarily the same thing as saying that supply and demand are actually sort of perfectly balanced in any obvious sense. And so in particular, if you were to kind of plot out how these different things behave, what you think of as balance could actually fall, in some intermediate range there. It obviously will not be at the extremes where lambda over tau is very large or very small. So that's one comment. And I think the other thing I'd point out is that in part, this will be dependent on how we're interpolating between the extremes. So remember, I told you that the way we construct our TSR estimator is that we use market balance to estimate, to come up with a value for what the customer side randomization and the listing side randomization allocation should be. And we chose a particular approach to that, that essentially inside of it, what we're relying on is e to the minus lambda over tau is kind of the parameter that's governing what AC and AL should look like, with kind of an obvious way of setting it up so that AC and AL behave as CR and LR designs in the right limits. You could choose other interpolations, and probably that would mean that that bar in the middle would look different than it does there. So I guess my 2 cents on that is probably not to read too much into the fact that TSR has a little bit of an edge there. I think one of the things that I do want to go back to is that this improved TSR suggestion that we had, I think that actually there is a lot of promise with this kind of a strategy. This truly is, this is something which is mechanistically doing something interesting and different from any of the other estimators that I talked about, where it's really trying to use the data from the experiment to directly estimate these competition effects that we were describing. So that's where I see a lot of promise. And to the extent that one can move towards optimization of TSR or proving results about kind of optimal design and interpolation, I think it would involve probably reasoning along these lines.
Good, thank you very much.
So it's almost noon, so I think people who want to leave can leave, and I think people who want to stay for more questions. And if Ramesh is fine,
yeah, I can hang out for a little bit. CMAC, I think, had a question, so I can answer that.
Hi, Ramesh.
Hey, CMAC.
Really enjoyed your talk. Just a question about your model. There's kind of an asymmetry between the customer side and the listing side. I'm wondering what your thinking was behind that, whether that's sort of intentional, it's supposed to be more representative of the actual environment, or whether that was just a convenient modeling choice. And specifically, I mean, you have these customers arriving, but you have kind of a fixed static population of listings.
Yeah, I think that's a great point, CMAC. So yeah, I'd say, okay, first of all, there are some small ways in which it was helpful, I think, from an analytical standpoint. Now, with the benefit of hindsight, my thinking is that actually it would be possible to carry through a lot of what we did to a setting where you have an arrival rate of listings as well. So I don't know that that's necessarily fundamental per se. Another small comment I'll make, which is going to sound kind of opaque, but I hope the spirit of it makes sense. It turns out that if you actually write out what happens in the limits when lambda over tau gets small and lambda over tau gets large, it's kind of obvious that in a limit where lambda over tau gets small, what happens, you can write down the logit choice model of customers over listings, and you observe essentially that there's no more customer to customer competition. In the limit where lambda over tau gets large, actually what's interesting is that you get essentially something that looks like a logit choice model where the listings are choosing customers. And now in the listing side randomization, there's no competition from listing to listing. And so that symmetry suggests that even though this model has a finite number of listings and arriving customers, there is some natural symmetrization of the model in that mean field limit. But the main thing I'd point out, CMAC, related to your question, I think, and one of the things that bothers me in general, is that I suspect something that's genuinely harder relative to what we've done here are interventions that actually change arrival rates and holding times of listings. So that I think would get quite a bit more challenging. It would probably take you a little bit outside the scope of some of the stuff we're doing here. We do allow tau to depend on theta. At the moment, the work in the paper doesn't allow the experimental intervention to change tau for the treatment and control listing groups. It's just kind of a mechanical thing. The TSR design, for example, if I have a listing whose holding time is affected by treatment, it should really be based on whether or not a treatment or control customer was the one who booked me. And so then I need like an expanded state to track that. There's that. I think there's equilibration effects, like the stuff that Stefan Wager and Kwangju looked at that I mentioned, that I think also play a role in how listings would behave. The analog in their paper is they were motivated by drivers choosing how much to drive based on long run earnings estimates in ride sharing platforms. So the analog of that in our case would be, well, how many listings are available? That's going to be dependent on some long run estimation that the supply side does. So I think that's probably, if I was thinking about where the modeling needs to go to really do a much better job, listings are longer lived and make longer run entry decisions and equilibration decisions. And a model that properly tries to account for those things, I think, would look more complicated than what we have here.
Thanks.
Ramesh, we have one more question from Dave.
Sure. Yeah, Dave should say something, because I just have to tell everyone, Dave sent me an incredible email yesterday with tons of very useful feedback on our paper. So I just want to take the opportunity to thank you for doing that, Dave. That was fantastic.
Oh yeah, of course, thanks. I should say that I had been asked a few months ago to read the paper and had put it off for a long time. So this talk was a good excuse to actually do it. I guess I was just wondering if you could say a bit more about how the TSR estimator performs when there are different types of heterogeneity. I know that in the paper, this is like discussed briefly in an appendix, but kind of briefly, and I think the focus there is on variance and not necessarily on how the bias reductions vary when there's high levels of heterogeneity. And so, I guess there would be customer heterogeneity, listing heterogeneity, different types of heterogeneity. But just if I recall correctly, these figures that were in the talk are, these, like you said, kind of simpler setups where, there's one type of customer, one type of listing. So just, obviously it's simulations and it's hard to make general statements, but if there's a directional sense that things work better or worse when there's more heterogeneity in the market.
Yeah, that's a really good question, actually. I think sort of the main thing that we were focused on was the qualitative benefit that you can interpolate effectively between the two extremes using the design. And not surprisingly, since that's a theorem that doesn't depend on how heterogeneous or not the market is. I think it's kind of hard. I don't think I can make general claims about how heterogeneity is going to influence the relative bias. One of the reasons I would be slightly concerned about doing so without some more structured analysis is because I suspect there would be a lot of commingling there of how you had set up model parameters. And so in particular, I could probably make some of these gaps that I'm showing you in this plot right now look different. These could look different depending on how I'd set the parameters up, even in the homogeneous setting. So I guess that's not a very satisfactory answer, Dave, but I think maybe to turn it into a positive, I'd say I do believe that there's hope that one could get structured understanding of how the level of heterogeneity influences some of these things. We were especially interested in thinking about, one interesting thing your question opens up is what kind of heterogeneity is interesting. And I think there's kind of obvious types of heterogeneity where you just have additional types, but the treatment is sort of uniformly beneficial or detrimental. Then there's other more interesting kinds of heterogeneity where maybe you have two different types of listings, and one gets better and one gets worse with treatment. And at least, again, like qualitatively, when I talk about interpolation, and then the variance calculations, like all of that stuff qualitatively obeys similar observations of what I showed you in the talk. But I do think like some understanding of how interventions that are uniformly beneficial versus those that can be heterogeneous in their effect, how that might influence the bias we see. I think that is an interesting question to investigate. And then maybe the last comment I'll make, since that opens up the question of the model. The other thing that we've been doing some preliminary work on is robustness analysis when you actually change the choice model to look like something different. So we've been playing around with a model where customers sample a fixed number of listings from the market instead of sampling every listing independently with some probability. We primarily did that with the goal of understanding variance a little better, and you see similar performance there. As you might imagine, that will create different types of competition effects, and I think an interesting question there is, can you recover the same kinds of market balance results that we were talking about?
Thank you.
Great questions, actually. Any more questions from the audience? So I have one comment, Ramesh. I think this is like fascinating work. I work very closely with experimentation design in platforms, and these are like fundamental questions and very hard to answer. So great to see some like theoretical, like underpinning of these, underlying questions. So one more like a comment to add to it. Often, like another dimension of exploration is when you think of customer or demand side, right? So you have customers and they have different queries, right? Or searches they're doing over time, right?
Mm-hmm.
So when you think of this treatment set, you can either like randomize customers, or you can randomize also the query set, right? And again, there's some nuances over there. I'm wondering if you like thought about questions along that dimension.
So do you mean, yeah, like I can randomize at different stages essentially of the funnel?
Yeah,
is that what you're getting at?
Yeah.
Yeah, that's actually a really, really interesting question. I think it's related, frankly, to what it means to calibrate market balance too, because what is demand depends on where you're measuring in the funnel. You have like
exactly
outside demand, and then you have like actual point of sale demand, and same thing with supply. So yeah, I mean, we're starting some work that's significantly more applied than what I described here in actually like trying to implement some of these things. And I think these questions are coming up there. I don't have a good answer for you yet. I do feel like, for as much as I love the style of work that's in this talk, I just want to make sure I give people the right word of warning that sort of at the end of the day, there's very little substitute for getting your hands dirty. And so I think like the type of question that you asked, I feel like that's one of those things which I would really want to be thinking about context, specificity, and tailoring what we're trying to do to a setting where we're really thinking about the right point in the funnel to be doing this kind of stuff. I mean, for one thing, there's certain points in the funnel where actually interference is weaker by design, right? I mean, just a caricature of that is in my talk, where the choice set formation process has two stages to it, and the state of the market is most important at the point where the consideration set's being formed. So I think like there are interesting ways in which we can start to do, we can get much more clever designs once you're willing to open up the funnel and think about what the different stages look like. But I do feel like at some point it's important to swing to the other extreme from this talk and make sure that you're really close to the application.
Makes sense. Thank you so much. Any more questions from the audience? All right, I think if not, I think on a closing note, I mean, thank you so much, Ramesh. This was like really interesting talk, a great engagement from the audience. Thanks everyone.
Yeah, thank you all. Appreciate it. Take care, everyone.